Now what I am doing here, in line number 99, see I am pushing E1000 and I am moving E1000 to CR3. Note that this is actually a privileged instruction. Since the PL is 0, this executes successfully. Because currently the code segment, what is the code segment? As you see, the code segment has privilege 0 and it is set in line number here. So already when we enter the code, so this instruction will be executed correctly. So what I have done now into CR3, I am moving the base address of my page directory. So this is having the base address of page directory. Now I am enabling paging. So I am pushing the flag and it will work correctly because the stack is well within the limit. Now I am clearing the interrupt. Again, this will be successful again because I am a PL0 code. So when the paging is enabled, at that point of time an interrupt comes, it actually sort of becomes like an imprecise exception because we don't know whether the paging will happen there. Now the interrupt service routine, where it will go, where it will start executing, because you are in the middle of a paging. So at that point of time, I don't want any interrupt to happen when the paging is getting enabled, because we really don't know the state of the operating system, the state of the architecture. So we clear the interrupt flag. Here, and we actually keep the original whatever status here. So we store the state of the flags in the stack, and then I go and clear it, clear the interrupt flag in the flag register. Now I am moving the content of CR0 into EAX. I can't directly go and operate on EAX, I can only move values from there. Then I am setting the 31st bit. And then I am moving the content of EAX back to CR0. At this point of time, completely my paging is now enabled. Now the next instruction to be executed will be this jump instruction, because my A1000 page is identically mapped. If my A1000 page was not identically mapped, then the next instruction to be executed will be as per the translation. So it will go to some other page. But since my A1000 is mapped down to A1000, the page A1000 is mapped down to A1000, this will execute this. And why I do a unconditional jump here, because many of these architectures are out of order architectures. So there can be some instruction that is after this would be still in execution, would have started execution. There will be some instruction before which is still to get completed, and we don't know which status it is. So we would like to completely disable those instructions, at least the one that is happening after this. That is very, very important, because those instructions have to now execute with paging enabled. And if they are progressed to some level, and then what would happen there is that they will start executing as if paging is not enabled, and that can basically lead to some program incorrectness. So it is very important that we flush the entire pipeline, specifically in out of order execution processes, to see that the execution is actually correct. So once this is all done, you now have a page directory in 0xE1000 and a page table at 0xF1000, as we had demonstrated earlier. Now you see what I am going to do. Now I am going to start executing this program. So here I am going to make C. So it has executed here on the left hand side. Now what execution happens? I am doing GS colon FFFF0C020. Note what is GS? Please note that GS has 0 as base and limit as very large limit. Okay, 5 Fs. So this will go to FFFFC020, and I am moving the word AAA. But FFFFC020 may not exist in your system. So this FFFFC020 essentially has to get translated. How it gets translated? Please note that your page directory index would be the last 10 bits, which is 3FF2, and your page table would be the next 10 bits, which is 3FC, and right shift by 2 bits, because each entry is 4 bytes, and then the offset is 20. So now we have to go and look at 0xEFFC, x/x 0xEFFC. Please note that that is pointing to F1000, and now you see that this has become 3. If you had noticed earlier, it was 1. Now why it became 3? Because the access bit has become 1. The architecture, because you have accessed this page, this particular instruction has accessed this address, this entry in the page directory, and that is why we see that this is F037. And when you study operating systems, there you will have some replacement strategies like least recently used, etc. This access bit can essentially give you some indication of which are the pages that were accessed at the recent past. Because the program is executing, after the program executes, it probably generates a page fault. Now the page fault handler has to basically start executing. At that point, it should know which page has been accessed in the recent. So this access bit can give information to the operating system, especially the interrupt service routine of the operating system, which is the page fault handler, to basically tell these are the pages that have been accessed. So this access bit is very important. Now from this I go to the F1000 page, and there, now what is the page table entry there? It is FFF0. Okay, because 3FC right shift by 2 bits will give me FF0. So I'll go and see x/x 0xFFF0, and note that this is again mapped down to the B1000 page. Now what this particular instruction in line number 120 should have done, it should have made B020 as a, yes, it has made B020 as a. So this is a very huge address, but through page translation I have gone and made B020 as this. This maps on to B020. So this basically explains you how this, in architectures they call it as page walk, how the page walk actually happens in the x86 architecture. Now let us go and see. I want to generate a page fault, and I already told you that the page corresponding to FFF8, I'll repeat this, is not available. So that we actually saw it was not. Now the page fault handler has handled this. Now let us go and see. When we did in the previous thing, what has happened? We saw that this FFF8 page was not present, right? And so then what happens when this particular command executes? Immediately the page fault is generated. The page fault number is D. Page fault number is E. And your interrupt service routine is at 0x, interrupt descriptor table is at D200. So sorry, D210. Your IDT is at D210. So now we are looking at x/2x 0x D21E. Right, D210, 14th one would be 14 into 4. It should be 14 into 4. That is 338. So 38 would be the entry. So D248. 2, 4, 8. Okay, and this essentially says the D248 is the entry, and the interrupt service routine is at this is the code segment 0008. This is a code segment, and within that code segment I need to go through an offset of 334F. Okay. Now where is the code segment? What is 0008 code segment? It is 8000, and from there I have to go to an index of 334F. So D34F would be the interrupt service routine, right? No, I think we have to do a little more calculation. The page fault, let us just go and see what is the page fault number. So let us go to this. Let us undergo this thing. Interrupt number 11 is segment not present. Interrupt number 12 is stack fault. Interrupt 13 is general protection fault. Interrupt 14 is page fault. Now 14 is actually E. So 14 into 4 bytes each, that will give us 56, and 56 is 38 in hexadecimal, and your interrupt descriptor table starts at D210. D210 plus 38, it should be D248 only, and so your interrupt service routine is at D3F4. Sorry, now where are we going wrong? I am just making some mistakes so that you can also realize what the mistake is. Each of this entry, how many bytes it is? 8 bytes long. So your interrupt descriptor table, it will be your 112th byte, not the 56th byte. So what is 112 in hexadecimal? It will be 70. So I have to look at 0xD280. Sorry. Right? Now you see that you have to go to the code segment 8 and go for an offset of 600. So what is code segment 8 here? It is code segment is 0x8. It has base at 8000, and then 600 offset would be 8600. Now this 8600, when it gets translated, will again be 8600 because it is identically mapped. This is also one of the reasons why the operating system page should be identically mapped. Otherwise you will end up in bigger problem. So what is 8600? Please note that when I do this align, so please note here I start with 8000 and I have done one align 200 here. Already it would have crossed 200 there, so this would have become 8400, and I do another align 0x200. So this is align 8600. So your page fault will start happening here. So this is your interrupt service routine for your page fault. And what we do here, so we just do some steps. We just put move gs colon 0x b1004 as this. So essentially to prove that I have entered the page fault handler. So what is gs colon 0x b1004? This is basically BC, 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 BC. So this is again, it will map on to 0x b1004 because the b1000 page is identically mapped, and there you see it as set up BC, 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 right. So it is set here, and then I just go and do a jump 0x8 colon 0x 200 here. So this will jump to what? Oh, sorry. So this is not so this is align 0x200. This is align 400, and this is align 0x200. Okay, sorry. So your page fault handler actually starts executing here. So it pops EAX. So what would be EAX? It pops the value from the stack. That will be the return address here. So that is EAX. Then now it moves GS colon B010 as ABCD DCBA. So let us see x/x 0x B010, and that is ABCD DCBA. Right. And then so it has entered the handler. Now to this EAX is going to be having so what I am doing here is I am moving the content of FFF8 to EAX. What I mean by moving the content of FFF8, because FFF8 is the page table entry in which we have marked the page as not present, and I go and test and set the 0th bit, because that is basically telling whether the page is present or absent. You know that initially it was B016, now it should now become B017, and I move the thing back to 0xFFF8, right? And then I do an IRED. So this pop EAX essentially pops out the error code, and then it basically goes to the page fault handler. It starts executing. It makes B010 as ABCD DCBA, and then it goes and takes that particular page table entry in FFF8. It makes that last bit 1. Essentially now the page will be present. It moves it back to EAX, and then what it does is it returns. When it does a IRED, we come back to the same instruction, right? The same instruction which is here, right? And now I go and execute this instruction. This instruction now will be successfully executed because the page fault is now handled. The page now has become present. So let me very quickly summarize what we have done. We knew that the page corresponding to this was not marked not present in the page table. I go and access this page, and I want to write into this page. This eventually creates a page fault. Page fault is interrupt number 14, which is going to be in the 112th byte in your page fault handler. So I go and look at the 112th byte. 112 is 70, so D210 is the first byte of interrupt handler, interrupt descriptor table. So I go and look at the entry at D280, and there I find that I am having the code descriptor 8, and I am having 600 as the base. So now with that I start executing at 8600. Please note that this is 8200, 171 line, this is 8400, and this is 8600. I first pop out the error code, then I just want to show the world that I have entered this interrupt service routine. So I go and see ADCB, DCBA, I move it to B010, which we have seen here, S/X0X B010 is this, and then we move FFF8. This is the page table entry. I move it to AX. I make the 0th bit as 1, essentially making page is present. I move it back to the page table and I do an IRED, and this IRED again comes and re-executes this particular instruction, and now you will see that this particular thing translates to B030, and now you will see S/X0XB030 as BBBB, which is done. The next thing is that I go and I just want to show that I am coming here. So I just see that BB, this FFFF C0, this actually maps on to B1000. So I'll just go and see S/X0XB1000. This has BC. So this just to again show that I am coming to this part of the code. Now I am jumping to a very large address 0x50 colon and a very high offset. So what is there in 0x50? So let us go and see S/X0XD050. So I should say 2x. Now this is a code segment of size 4 GB, right, with base as 0 and size as 4 GB. It's a large segment, and I am doing FFFF F400. So since I have 32 GB, I can go there. Now this FFFF F400 actually maps on to 8400, right, because your please note that this maps on to the page directory entry, which is FFFC, and so let us go and see S/X0XEFFC, and that is pointing to F0, and there I have S/X FFFC, and please note that this is also pointing to 8000. So I have one more additional page which is pointing to 8000, just to demonstrate this. Now this plus the last 12 bits is 400, so I have to jump to 8400, and note that we have done so this is align 200, this is align 400, so it will jump to this, and what it does, it makes B1004 as this thing. So S/X0X B004, and it has made it as BC. So it starts executing, and again it just jumps 0x8, 0x200. 0x8 actually starts with B1000, so it 8000, and it has to come to 8200, which is this. So after it finished this, it jumps back to line number 174, and there you go and disable paging, and you are happy to execute the program. So this is how the entire thing works. And just to have, where is our stack? So stack is at, let us go and see where our stack is. It is at CF100, and so let me just see S/, and its base is 0x100. So CF100 plus 100 is D0. So let me say S/10x 0xCFF0, and there you see that the stack had some activity. So it has pushed A7, it has pushed the code segment register, it has pushed some error code 002, etc. So this is where the stack has been active. This is from this point. So it doesn't touch D1000. From CFFF is where the stack is active, and you see some stack activity there. If you just say S/20x 0x CFD0, right? Sorry, it is yeah, CF D0. Um, so there you see some lot of, so we have just loaded some random data here. But now you see from CFF0 and these points, this is where the stack has been pushing data inside. So you can now go and see the content of the stack and find out how the interrupts are handled. Okay. So I hope you understood this particular assignment. Please go through this again, my lecture. And also please be very good in your calculations. So a lot of times I have made certain voluntary errors, and just to tell you where you can also go around. A typical error that an assembly programmer does when he's trying to look at coding is what I have also done here. So those errors you should be very careful, and if I don't do that error, it will not come to you. So I have voluntarily incorporated certain errors and I have rewinded back. So please look at what errors I have done and how I have rewinded back, and that will also be a good learning experience for you. Let us meet in the next session. Thank you.